Okay, so the exercise is that we have a 2 by 2 matrix, and we're told these are the eigenvectors, and the eigenvalues are these values. So the idea is that because it says respectively, that the order matters. So the first value here, 4, is going to be associated with the first vector, 3 minus 5, and the second value, -1, is associated with the second vector. But all we know is that this is a 2 by 2 matrix. Okay, so first, we're going to introduce some notation. We're going to call V1 3 minus 5 and lambda 1 is 4. And those two things are going to be associated with each other. Sorry, I have a lot of things here going on. So let's see. Okay. So these two things are going to be associated with each other. The lambda 1 equals 4, and then this vector. And then we have, we're going to call the second vector v sub 2, and that's going to be associated to that value of -1. So the definition of eigenvalue, the definition of eigenvalues has to do with an equation of this type, okay, which is called the eigenvalue-eigenvector equation. Because here we have a matrix, we have a vector, and in the left-hand side, and in the right-hand side we have a scalar lambda, and then we have vector v sub 1. So both of these equations, which I'm calling here equation, this would be equation 1, and this here equation 2. They're both things that look like square matrix times a column in the left-hand side, and then on the right-hand side you have a scalar times a column. Okay, so they're both vector equations. So on the left-hand side we have a vector, and on the right-hand side we also have a vector. So the only thing is that we don't know what the matrix is. So we're going to say, look, let's suppose the matrix, we could call the entries something like A11, A12, A21, and A22, okay? But instead of using that notation, we're just going to simplify the notation and say, let's work with letters A, B, C, and D in that order. First row A, B, second row C, D. Those are the entries of the matrix, and those entries are supposed to be unknown. So the first thing we do is that using equation 1, we're saying, look, this is A times V1 equals lambda 1 V1. So in this eigenvalue and vector equation, we know V1, we know lambda 1, right? So the right-hand side is something that we can compute with values. And then in the left-hand side, so that's what we do here first, right? So when we do this lambda V1 scalar multiplication, we obtain this vector that has entries 12 and -20. And then when we do the matrix A times vector V1, then we obtain a vector, okay? And this vector has entries 3A minus 5B and 3C minus 5D. So in using equation 1, we now have another equation that I'm calling here equation 3, which is a vector equation, and is given by this. So are you with me?
Yes, I am.
Okay, so now we use equation 2. Equation 2 was AV2 equals lambda 2 V2. So we're going to use, we're going to write the matrix A as A, B, C, D, and here is V sub 2, and on the right-hand side we have lambda 2 and V sub 2. And again, the right-hand side here is something that we can right away compute as a vector that is going to have entries -2 and -1. And then the left-hand side is also a vector, but now it takes the form 2A plus B in the first entry, and 2C plus D in the second entry. So, and now I'm going to call this equation 4. So what we can do with equation 3 and equation 4 is rewrite those equations. So let's see. We rewrite equation 3 and 4 so that every equation would have all the unknowns, A, B, C, and D, and basically we just have to use 0 coefficients. So that would give, so basically the first two expressions here, they come from 3, and the second two expressions come from equation 4, right? We're simply now using these coefficients, zero coefficients, for unknowns in expressions where they didn't seem to appear, but we know they appear there. And so once we write this, we have, so in this whole enchilada here, we have four equations, and we have four unknowns or four variables. Okay, so we could write this in matrix form, matrix vector form, and now the vector of unknowns. So these are the variables. The variables are A, B, C, and D. We have a 4 by 4 matrix of coefficients, and then we have this other vector of constants. So once we do that, then we can form the augmented matrix and compute the reduced Rachel form. So this last column here is the column that contains the constants. We row reduce. I did this beforehand, right? So there are, here you can use one of those RIF calculators, or you can do this by hand. But what we are interested in is knowing. We're going after the solution set. So is the solution set empty? In such case, not such values exist. This matrix does not exist. Or does it have at least one solution? In this case, is one solution set that has one solution only, and then these values 2 or 13, negative 30 or 13, those are the values of the unknowns. So now, by computing the solution set with reduced Rachel form, we determine what are the values of A, B, C, and D.
Okay.
And this is it. But since, as a little treat, so that you don't get bored, okay, so here's the matrix A. There are 4 entries. That's not a little treat. This is the little treat. Verification, okay, just for practice. So if we wanted to verify, the verification is, well, if that is truly the matrix we're going after, then the eigenvalue eigenvector equations should be satisfied. So we should verify that A V1 really is equal to lambda 1 V1, and similarly for V2 and lambda 2. So we compute the matrix product, matrix vector product A times V1, right? So here is A times V1 is right here, and that calculation, there are fractions here, so this is juicy and entertaining, and you will not get bored. So that gives you a vector that looks like this, with entries 12 over 20. And if you compute lambda 1 V1, so here's lambda 1, 4, there is that vector 3 minus 5, and that also gives you this vector. So this is a way of confirming that truly A V1 matches lambda 1 V1. So our calculations of what matrix A is are reassured by this, and then you can also verify the other eigenvalue eigenvector equation, which is A times V2. That gives you this vector, and then you also compute lambda 2 V2, and you see that there is a match. Okay?
Okay.